code for so that others can see the lesson later, right? All right, Kelly, you can mute your mic. It's okay. So, what is density? Define density. How do you want to define density? Do you want a formula or in words? Kelly, I'll start with you. How do you want to define density?
Both
Both. Why both?
in words and by formula.
Which one is
I
easier?
should not be. For me, I think both of them are easy.
Oh, okay. So this is a question from I think let's see, is it oh, this is a question from was we're doing meta. So it's a question from the paper November 2025. So this is November 2025, paper 3, right? So it's the number 4.
Mhm.
Okay, because we are doing meta, so we're raising some questions. So we can say density, right, is equal to mass over volume, right? So density is equal to mass over volume, right? So distinguish the second part, distinguish between water at 20 degrees Celsius and ice at minus 5 degrees Celsius in terms of spacing and motion of molecules. So how do you distinguish the two? Water and ice. Water at 20 degrees and ice at minus 5 degrees Celsius in terms of spacing and motion of molecules. Believe. How do you distinguish between the two? Okay, she's unresponsive. Kelly, you can tell us.
Okay, I think we use the force of attraction between the molecules. Yeah, also include the absolute zero
What
and
are
the
the force
triple
of
point.
so this is just water at 20 and then ice at minus. What do you mean force of attractions? What are the forces of attraction between water at 20 and then ice at
So
minus 5?
at 20, the water, I think the water would have gained um some heat energy. So
Mm.
the particles tend to be more mobile in
Uh,
mobile form, and
okay.
the forces of attraction are weak than those of the ice at 5 degrees.
Is that true, madam?
I'm not sure, sir, but I'm just trying.
Okay. All right. In terms of spacing, so ice is a solid. This one. It's a molecular solid.
Mm.
And then water is a liquid. So in terms of spacing of molecules, what can we say about spacing of molecules? So water at 20 degrees, right? Remember, it's a liquid, right? When we introduce phases of matter, right? When we introduce phases of matter, we know that a liquid, it is the liquid particles are in motion, right? Are in random motion, but the force of attraction are still great enough, right, to hold the water particles, the liquid particles in the liquid body, right? And then in the solid, it's different from the solid, right? It's different from the solid particles, right? The solid particles they are confined to the structure, to the molecular structure. They can only vibrate about their equilibrium positions. So that's the motion of. So they only have, in terms of internal energy, ice, the particles in solid, anengangori ne vibrational kinetic energy, but in liquid, anengane vibrational and translational kinetic energy, both they can vibrate and they can also move, right? And then the spacing, they're closely pegged in ice, right? and then the liquid, they are evenly spaced. Stating two differences between boiling and evaporation. Believe, are you there? Want any two differences between boiling and evaporation? If she doesn't respond, Kelly, you can tell us what are the differences.
The differences between boiling and evaporation. Boiling, it takes place at 100 degrees, at a fixed temperature of 100 degrees Celsius. Then evaporation, it takes place at any given temperature. As well, boiling, it happens throughout the liquid particles, and evaporation only happens at the surface of the liquid. I think.
Okay, yeah, that's correct, right? So boiling occurs at a fixed temperature, right? And then evaporation occurs at any temperature. Okay. So the other difference, right? So the other difference that you have left out is that evaporation leaves the molecules that are left behind, they are cooled. But the boiling, when the molecules are left behind, they are not cooled, right? Remember, there's cooling. So we're saying in evaporation, there's cooling of the molecules left behind, but in boiling, there's no cooling, right? Okay, did you get that, Kelly?
Yes, yes, yes.
Yes, okay. So then part B, what are the characteristics of a good thermometric property? What are the characteristics of a good thermometric property?
I think it varies linearly with temperature.
What do you mean? Huh? What do you mean?
You say
It varies linearly with temperature.
yes.
What do you mean? Can you please
Mm.
elaborate?
So, mm, um, if temperature changes, I don't know how to put it, but
All right, if temperature
please help
increases,
me with.
I've opened. Uh, Continue.
Um, mm, it is if something is in linear motion, which means they are directly proportional, right? In other
I'm just.
words.
Oh, Believe, do you have something to say?
Yes, I do.
Okay, say it, please. Tell us.
I think
Yeah? What do you think? All right. So what I think what is she's trying to say is that we say that a good thermometric property, so the first characteristics that it must be we say monotonic, right? Monotonically increasing or decreasing, right, with temperature, right? So if temperature increases, the thermometric property is to increase. If temperature decreases, the thermometric property is to decrease, right? That's the first characteristics. And then the second characteristic is that uh, an increase in temperature should produce a large change in the value thermometric property, right? So we're saying a small increase, the temperature ikaita a small change, and tofana kuwana, let's say if the thermometric property is a resistance of a wire, let's say platinum resistance, tofana kuwana a great resistance for a small temperature change. That's the second characteristic, right? Did you get that, Kelly?
Yes, I did. Thank you.
Okay. So we're saying small temp increase, right? Must induce a large change, right, in the property, in the thermometric property, right? So describe the structure of a thermocouple thermometer. Can someone describe the structure of a thermocouple thermometer or a thermoelectric thermometer? Anyone wants to try? Kelly, believe is not available. I don't know what's wrong with the network.
I'll try. I think it uses EMF, right? So since the word couple, which means there are two different there's a, what should I say? A hot I don't know, and a
So
cold side.
also what is the thermometric property in a thermocouple thermometer?
Electromotive force.
Or EMF at a junction between two metals, right?
Yes.
So if you're describing the structure, you can just say it consists of two wires of different metals, right, joined at the ends of junctions, right, at two ends of junctions, right? So if there's a temperature difference between the two junctions, an EMF is developed. So an EMF is set up if there's a temperature difference between the 2 points, the two junctions. So that's how the thermometric property works. So remember if you watch the video I did on the comparison when I was comparing the thermometers, the disadvantage of a thermocouple was that it uses a millivoltmeter. So to measure the small EMF changes, so we need a millivoltmeter. So there is to be a millivoltmeter connected per thermocouple. And is that so?
Okay.
Okay.
Yes.
So a platinum resistance thermometer is found to give resistance values of 3.5 ohms at ice point and 4.80 ohm at steam point. Determine the resistance at a temperature of 10 degrees. Okay, so what's the formula for when you're at empirical centigrade scale of temperature? What's the equation when you are looking at a resistance thermometer? What's the equation for the empirical centigrade scale of temperature?
Or the thermometric equation. So I think is theta minus theta L over theta U minus theta L equals
The
to
resistance,
X
remember.
minus X.
So this
Okay.
is a resistance thermometer. So we use the Toshansas with specific, right?
All right.
100 degrees. So the temperature is equal to resistance at temperature theta minus resistance at, so this is supposed to be 0, minus resistance at ice point over resistance at 100 degrees Celsius minus resistance at ice point. So we want
Okay.
we want r theta here. So the equation becomes 10 is equal to r theta minus, so it's r theta minus resistance at ice point is what? It's 3.50, right? So it's 3.50 over resistance at steam point it's 4.80 minus 3.50 times 100. Can you work that one and tell me what is R theta? What is R theta? So this becomes an equation, right? Can you solve the equation and tell me what's R theta?
Okay.
Okay, so it becomes 10 is equal to R theta minus 3.5 over 1.3 times 100. What is R theta? What's the answer?
F from there we have R theta minus, I can't see.
3.5. It's R theta minus 3.5.
Okay. All right.
Yes, so what's the...
I got 3.63.
3.63.
Yes.
Okay, yeah, that's correct. So it's 3.63 ohms, right?
Yes.
So it's 3.63 ohms. Okay, that's good. Okay, so now we are left with 7 minutes. Only left 7 minutes. Let's do the last question. Set the assumption for the kinetic theory of gases that explains why the internal energy of ideal gases is wholly kinetic. What is that assumption?
For mm,
Remember, those assumptions to the kinetic theory of gases?
yes.
Have you watched the video on what did I it's on ideal gases?
I was in the process of watching.
No, it's fine. So what is that assumption?
Since these gases have a high kinetic energy but a low potential energy, so the
So I say
assumption
the theory, the assumption is that an ideal gas, right? It's free. The intermolecular forces are negligible. That holds the gases, they are negligible. So the assumption is that the gas is free. So the molecules are not bound to any intermolecular forces. So there is no potential energy. So the potential energy is negligible. But this is also the ideal gas. It is what? It is negligible intermolecular forces. So that's why it is wholly kinetic. Remember, what is internal energy? What's the definition for internal energy? Okay, internal energy is the sum of the random kinetic and potential energy of the particles that make up the system. So that's the definition of internal energy. It's the sum of the random kinetic and potential energy of the particles that make up the system. So I to ideal gas, the assumption is that it has no potential energy, right? Because of we're saying it is negligible intermolecular forces. So potential energy, no, that's zero, right? So let's say we have an equation, internal energy U is equal to EK plus potential energy, right? So potential energy becomes zero for an ideal gas. So internal energy is only given by the kinetic energy. Ubabata, are we clear?
Mm-hmm.
What
Yes.
form of kinetic energy is that? What form of kinetic energy?
Mm.
There's vibrational
Not sure.
kinetic energy. There's vibrational kinetic energy. I've said it. It's in what? It's found in solids. Solids just vibrate about their equilibrium positions. And then which form of kinetic energy is found in liquids? I've just mentioned it. If we are paying attention.
Mm. They also. Mm, I'm not sure.
So it's translational kinetic energy.
Which one?
Translational,
Okay.
because liquid particles, they can move. They do not only vibrate, but they can also move. So it's translational kinetic energy. So gases, they've both vibrational and translational kinetic energy. They can move gases, they can vibrate, right? So they've both translational and kinetic energy. Right. I wanted to do the rest of the question, but due to our time, the time is up. So we'll just do it. I think tomorrow. Yeah, we'll finish. We'll just do the rest of the questions tomorrow. So this was November 2025, paper 3, right? So any questions? Are there any questions?
Mm, no. So we have. Can I ask? We have two. We have those two types of kinetic energy.
Mm.
Okay.
Okay.
That's my question.
Okay. Okay. So if there are no further questions, I think you can. That's the end of the lesson. And
Okay. Thank you so much.
okay, thank you for your time.
Oh.
Okay.